All right, good morning, pre-calc. Let's get ready for the do now. Today's do now is actually story time, so you don't even need to get a piece of paper. Once upon a time, Princess Buttercup ruled the kingdom called Florin. In the kingdom of Florin, there are two Graf seaports. Each port was a home to a dread pirate. The dread pirate Leslie lived at the left end of the world, in a place called Port Minas. He would sail from the left to find the height of the ocean. The dread pirate Roberts lived at the right end of the world in a place called Port Plus, and he would sail from the right out to find the height of the ocean. The oceans in Florin are weird, sometimes discontinuous, meaning they don't always attach to one side to the other. And Princess Buttercup was especially interested in the unusual, the curious things she'd never seen before, maybe things that don't always make sense, like the Cliffs of Insanity. So when Princess Buttercup wanted to find out how high the Graf Sea was at a certain place, she would send orders to the dread pirates to sail from their ports to that place. Sometimes she'd only send orders to one pirate or the other pirate, sometimes both at the same time. The dread pirates would sail out to the place she said to go to and then report back the height that they found. And Princess Buttercup would find out if their measurements agreed with one another. Also, by the way, speaking of graph seas and dread pirates, open dots on graphs, holes in graphs, discontinuities in graphs, none of that stuff matters to pirates, right? They just sail arbitrarily close to a point, and that's an actual math word. It's not just because I wanted to say arr. They sail arbitrarily close to a point. It doesn't matter if the point exists or doesn't exist. Graph pirate ships follow different rules than graph walkers do. That's why we have graph pirates. Otherwise, we just use graph walkers all the time. So, the end. Also, bonus points if you know what movie I just ripped off. So, Dread Pirate Leslie over here on the left, Dread Pirate Roberts over here on the right. Princess Buttercup will say, I want to know how high the Graf Sea is at this one point, and she'll send orders. Dread Pirate Leslie sails from the left side towards the ocean. Dread Pirate Robert sails from the right-hand side towards that spot in the ocean, and they'll find out what they see. Also, if you've never seen the movie The Princess Bride, it's super, super old, but absolutely, positively worth watching. Here's Princess Buttercup, Dread Pirate Roberts, and Dread Pirate Roberts' ship, Revenge. Also, the movie is absolutely nothing at all like the story I just told you. I just told the characters, plus made up another one. So, more do now. This part you do actually get to do. We'll go ahead and answer this out loud. I mean, honestly, nobody is around. They won't hear. So just go ahead. 1, 2, 3, and 4. On your mark, get set, go. Okay. So number 1 is the left end, and negative numbers there. Number 3 is the right end, and positive numbers go there. So pirates don't always know. They don't always know to write, and so they'll be like X marks the spot. They just make their mark without actually knowing how to write their name necessarily. So same is true for these pirates. Dread Pirate Leslie doesn't actually maybe know how to spell his own name, but makes his mark is a minus sign, and the Dread Pirate Roberts. His mark is a plus sign. And today we're going to be learning about limits. And so our learning target is you'll be able to use limit notation to find the following things. Left-handed limits, right-handed limits, two-sided limits. And let's find out what the heck that even means. So first of all, the definition, a limit. A limit is the function value, the y value, or the height that a function approaches as the input approaches some specified x value. Okay, so we use limits to describe what is happening to a graph when maybe a graph has an asymptote or heads towards infinity. Perhaps there's a discontinuity, there's an open dot on the graph, some kind of hole. where you're not actually going to be able to arrive at a certain x value because maybe the graph doesn't exist there. But when we look at the graph, we can say, well, if I were walking along the graph or sailing my pirate ship along the graph, as it were, it'd sure seem like I was heading towards this height. That's what limit notation is all about. It's like where it looks like you're heading towards. And whether the graph actually exists there or arrives there is not actually something that limit notation takes into consideration. We've got plenty of other notations that do that kind of thing, and we've already learned them and been using them, interval notation and coordinates, those kinds of things. When the graph actually exists, those other notations work. So here's what limit notation looks like, plus some words. So this part up here is what limit notation looks like. It's got a couple of different parts we want to pay attention to. So when we write that limit notation, the word limit obviously is too long for mathematicians, so we truncate that to just 3 letters. So just LIM. Underneath that is the x coordinate that Princess Buttercup says, hey, pirates, go there. So x approaches, that's the arrow, approaches some a value. That's our x coordinate. All right, so the pirates are going to head towards that x coordinate on the graph. It doesn't matter whether they actually can arrive there or do arrive there, whether the graph exists or not. That's not the point. The point is that's where they're headed. And then the other part of the function notation, the other part of the limit notation looks like function notation. So the value of the function f of x equals, or sometimes this is not an equal sign. Sometimes it's written with an arrow. It's just a matter of what textbook you're looking at. Really, they both mean the same thing. There is not a difference. They just are written differently. And so this L, that is the y coordinate, where we're going to look at the graph and say, hey, the graph is heading towards this height. And whether it gets there or doesn't get there, whatever, that's not the point. That's where it looks like it's heading. And so the A is going to actually be a number. We'll be given that, and that tells us where to look on the graph. That L number, that's our answer. So we're going to write down the y coordinate over here in the red highlighted area. Okay, so there's limit notation. So when the limit is just from one side or the other side, we call it either a left-hand limit or a right-hand limit. So if Princess Buttercup says, yo, Dread Pirate Leslie, I want you to start at the left side of the graph and sail out towards this one spot, whatever height the Dread Pirate Leslie finds, that's called a left-hand limit. Leslie, if you've actually seen the movie, you know that the character's name actually is Wesley, but you can't use a W to stand for the left side of the graph, so poetic license. When you approach the graph, you approach a point from the right-hand side when the Dread Pirate Robert sails out towards the ocean to follow Princess Buttercup's rules. That's called the right-hand limit, and ignore the pirates altogether. Grab onto that graph with your right hand. Where your thumb is pointing along the graph, you slide along the graph. That's the right hand limit. Grab on there with your left hand. Wrap your fingers around the graph. Follow that along wherever your left thumb is pointing. That's going to tell you what the left hand limit is. The two-sided limit, this is our third part of our learning target. The two-sided limit only exists if both pirates find the same value, which means the two parts of the graph have to be connected. If you have two parts of a graph that are discontinuous and they don't connect, they're pointing at different spots, you're not going to have a two-sided limit. Okay, but if the two sides of the graph come together and the graph is connected there, if it's continuous, then we're going to get a two-sided limit, which is whatever height the graph is connected at point A. So two-sided limit only exists when the Dread Pirate Leslie and the Dread Pirate Robert see the same height. They sail out to the ocean sea, or the graph sea, and they find the same height. All right, well, let's do some examples. So here is a graph. You can see it is discontinuous. I got one side up here, not attached to the other part of the graph. Okay, graphs are sometimes discontinuous. In the first several years of high school math, you don't deal with discontinuous graphs very often. Okay, here they are. So we've got an open dot, a closed dot, a whole bunch of stuff going on. Okay. Well, limit notation is built for situations like this where there's weird stuff going on and we're going to describe it. So the right-hand limit in blue is indicated. This is important. How do we know it's the right-hand limit from the notation? It's got this tiny little plus. It's written like an exponent would be written. It's not an exponent, but that's like that tiny little superscript notation above the 1. So x is approaching 1. That tells us what x coordinate to go towards. And the little tiny plus sign, that tells us that this is a right-hand limit, because the Dread Pirate Roberts is sailing from port plus over there on the right side of the graph. So when Dread Pirate Roberts sails his Dread Pirate ship towards that x coordinate of 1, it really, really looks like he's going to end up at a height of 1. And in this case, he actually arrives there, and that totally doesn't make any difference. There's a closed dot. The graph actually goes there. It doesn't make any difference. You're going to move Roberts out of the way. So the green one, the left-hand limit, has this tiny little minus sign. I made it a little bit bigger just so we could see it easier here, but that little tiny minus sign is written in the spot where an exponent would go. It's a little superscript minus above the 1. Tells us that we are approaching from the left side. We are the Dread Pirate Leslie sailing from port minus. All right, so Dread Pirate Leslie starts from the left side of the universe. Sail, 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 sail. And as he approaches the x coordinate of 1, it sure looks like he is going to arrive at a height of 3. Can he actually get there on this graph? No, because there's an open dot. And that does not matter for limit notation. Limit notation is built to basically ignore that and say, whatever. If you kept going, you look like you'd get to 3. Right? Okay. So in this case, the right-hand limit and the left-hand limit are not the same. The two Dread Pirates do not find the same height. They tell Princess Buttercup 2 different numbers, and so the two-sided limit does not exist. All right. Lastly, since limit notation does not deal with the part of the graph where it exists or doesn't exist, it just says, look, this is where you're heading, then we also want to know what is the actual function value, because the limit notation doesn't tell us anything about whether the graph does exist or doesn't exist, whether it's an open dot, a closed dot, an asymptote, or whatever, right? And so often we will also be asked for the function value so that we can say, you know what, it's heading here from the right-hand side, it's heading there from the left-hand side, but we want to know, where does the graph actually exist? So if we had a little graph walker and the graph walker tried to stand on the open dot, it's going to fall through the hole. You can't stand on an open dot. It doesn't exist. So where does the graph walker actually stand at an x coordinate of 1? That's going to be on the closed dot. And so the function value for that is 1. That is the height. The height is 1. So let's see another example. Let's start with the right-hand limit. So right-hand limit, it's got the little plus sign. So I'm looking for an x coordinate of 0. And so the Dread Pirate Robert sets out from the positive side of the graph, sails along the graph until arriving at an x coordinate of 0, or nearly arriving at an x coordinate of 0. And it sure looks like that if he kept going on the course he was on, when he got to an x coordinate of 0, he would have a height of 1. And we know that he doesn't because there's an open circle on the graph right there, but it sure looks like that's where he's heading. Let's get him out of the way. For the left-hand limit in green, so again, I have this little minus sign up there in the spot where the exponent would be. That tells me, out of this whole entire notation, that's the only thing that tells me it's a left-hand limit. And so the Dread Pirate Leslie starts off from the left side of the graph at port minus, sail, 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 sail. And as he approaches an x coordinate of 0, sure looks like he's heading for a y coordinate of 1. The two-sided limit, I don't think I mentioned this before, but in the notation, the only way you can tell that it's a two-sided limit is that there is not a little plus or minus up there in like the exponent spot on the 0. It just says 0. So that's the two-sided limit notation. And in this case, we can look at our previous answers. They're both the same, and so that means that there is a two-sided limit. It equals 1. what if we hadn't actually been asked those questions before? What if we just had this graph and it said, what's the two-sided limit? Well, then we could look at the graph and we would see that both sides of the graph are connected and they're both heading for the same place. And so it's going to tell us that wherever they're heading for, that whatever height it is, that's the two-sided limit. So both boats, in this case, both of those pirate ships, is heading for the height of 1. So that is our two-sided limit. And again, with limit notation, the open circle, closed circle thing, totally irrelevant, makes no difference for limits. Practically everything else we've ever learned, it makes a difference, but not for limits. And that is the reason why we are usually asked for the function value in conjunction with all of these limits. So the function value at 0, our little graph walker is going to go and stand wherever he can actually stand on the part of the graph that is standable, which is going to be the closed dot. It's a weird floating closed dot, but the height of the function at that spot is 2. So that is the function value. Next example is the Reyes for this graph, which again is discontinuous. And so for the right-hand limit, Dread Pirate Roberts is going to start off from the plus end of the graph. We got that tiny little plus sign there. And so, oh no, I lost the boat. And as Dread Pirate Roberts sails closer and closer and closer towards an x coordinate of 1, it sure looks like they're just going to drop off the bottom of the graph, going down forever towards negative infinity. And for the left-hand limit, we get the little tiny minus sign there. We're looking at x approaching the 1 from the left-hand side. And so the Dread Pirate Leslie is going to sail towards an x coordinate of 1, following the graph. Whoop, and as you get closer and closer and closer to 1, the graph bends further and further up, infinitely far up into the sky. That's a weird thing for an ocean to do. So it's going to be positive infinity. So I know we've used infinity for lots of different things over the last week or two. And with limit notation, the number that you're writing over here in my little answer box is a y coordinate. So up is positive and negative infinity refers to down. So now with other things that we have talked about with interval notation, we were talking when we wrote something, we were writing the x coordinate, and so negative infinity meant left and positive infinity meant right, and the same with maximum and minimum. And this is not any of those other things, which is confusing because different, right? So I'm writing down the y coordinate, the function value, the height, and so in the vertical direction, negative is down, positive is up. Okay, so the two-sided limit, the limit of the function as x approaches 1, with no tiny little plus or minus in the exponent spot, that's the two-sided limit. And in this case, the two Dread Pirates do not find the same thing. One's going up, one's going down. If we look at the graph, it does not connect. It is discontinuous. The two parts of the graph are not attached there. Or we could look at our previous answers for the right-hand limit and the left-hand limit and see that those are not the same answer. So the two-sided limit does not exist, DNE. Lastly, function value at 1. If we put a graph walker on our graph and try to have the graph walker stand on the graph at 1, it can't. There's nowhere to stand. The graph does not exist. This is an asymptote. If you're on this branch of the graph, you could get pretty close to 1, but you never actually arrive at 1. And if you're on the other side of this other branch of the graph, the graph walker obviously would be moving from left to right. And so at the very beginning part here, you'd be really close to 1, but still never actually there. The graph has an asymptote, does not actually exist any place at an x value of 1. And so we can try to get our graph walker close, but with graph walkers, close doesn't cut it. So this graph does not exist any place at an x coordinate of 1.